Hello everyone, my name is Rajat Sharma and today I am presenting my phase 2 work for my thesis project, and the topic of my project is estimating remaining useful life and the state of health of EV batteries by hybrid frameworks. The mentor of my thesis is Dr. Sandeep Talesar. So let's start with some introduction and motivation. As we know, we are transitioned to some EV or electric vehicles, and batteries plays some crucial role in that transition. And we also know that they degrades in non-linear way, so which leads to two type of challenge when we overestimate their health, so which leads to some unsafe charging and thermal risk. And the second one, when we underestimate the health, which leads to some economic risks or a financial factor also there. So when we if we underestimate the health, we retire good batteries too early, so it leads to some financial risk also. The objective of this thesis is to develop a lightweight framework which is suitable for resource constrained battery management systems, like the microcontrollers used in some standard electric vehicles. So when I did literature survey, so I found two type of approaches, or more of the two extremes. First one is the model based approach, where we have some electrochemical equations, morely like partial differential equations. We can use them, but they are computationally very intensive. Second one is data driven approaches, like transformers or LSTM. They are accurate, also state of art, but they require too much data set, and the memory footprints are too high for these transformers. So we have the research gap. Although we have some existing pins also, but they are also using partial differential equations in their loss functions. So they also are computationally too intensive. So I found some research gap, so where I can develop a lightweight framework where I can use ordinary differential equation in place of partial differential equation with some GRU. And I am also doing this dynamic loss balancing. So let's start. So in problem statement, I am estimating state of health of battery. Here I define them, and I also ensure to predict it with good accuracy, and the the degradation should follow some physical laws, like some thermodynamic laws. It degrades in a monotonic way. So as I said, I'm not using partial differential equations for, because those equations are too computationally intensive. So I'm using these two ordinary differential equations. These are simple, yet given like good result. So first one is the Verhulst or logistic model. The second one is double exponential model. It captures the knee point. Knee points is a point where the battery degrades like too fast. So it it creates some new points. And so I have two type of data sets, so I am using these two models as in my loss function. Sorry. As a solution strategy or a methodology, I'm first ingest all those parameters. I'm using these two NASA or Kelsey data set, and after pre-processing I will do some smoothing, Septic Gole filtering, and then I will extract features like ICA, incremental capacity analysis, and then as a deep learning backbone I'm using GRU. I can also use LSTM, but GRU is simpler and yet comparatively same. So I'm using GRU because the parameter counts are less, and which leads to less memory footprint. As an optimization challenge, I'm using some adaptive weighting. So instead of create a manual weights or static weights, I'm using adaptive weighting in my loss function, which learns and then update itself. As a in data set, I'm using these two data sets. First one is coming from NASA, which is I'm using these four series: B5, B6, B7, B8, and this data set I use this. I took this one because it has some like capacity regeneration noise, so it test my model robustness. And second one is Kelsey dataset coming from University of Maryland. So it has some knee points, so I can also generalize this result, like train on one model and test on second one.